to another screencast. We're going to go through the topic of logarithms today. It's an A-level subject, but something that's useful in its own right. You may well have found yourself having to solve problems like 5 to some power equals 32. Don't ask me why you might be wanting to solve that, but if you've ever got to a situation where you're trying to solve something like that, you might have only been able to resort to trial and improvement by changing different powers of x until 5 to that power gave you something in the region of 32. Now, logarithms are a way of solving this accurately and quickly. So here are the list of things that I intend to cover during the course of this screencast. So let's start straight away by thinking of the definition of logarithms. Well, very simply, a logarithm is an inverse of an exponential function. An exponential function is something with a power. You're familiar with them. It could be powers of 2, so for example 2 to the power of 3 is an exponential expression. That's clearly the answer 8. What we want to be able to do is introduce this idea of logarithms, and if I write an equivalent statement for this in logarithmic form, and then I'll generalize it in a moment. Written in logarithm form, that would be log to the base 2 of 8 equals 3. Now those two statements are equivalent, and initially when you first meet logarithms it's just a matter of taking that on faith until it becomes clear what it's all about. 2 to the power of 3 gives you 8. Equivalent statement is log to the base 2 of the number 8 equals 3. So we can see straight away the answer to a logarithm is the power that the base number here, 2, has been raised to. So logarithms can be used to find a power when you don't actually know what it is, the power that you're working with. Let's generalize that. If I said a to the power of x equals n, an equivalent statement in logarithmic form would be log to the base a of n equals x. Let's have a look at a graph for a moment. Here's an exponential function. This is the graph of y equals 10 to the power of x. This is an equivalent graph of y equals log to the base 10 of x, and you can see that they are reflections of each other in the line y equals x. So they're inverse functions. So let's try some examples just to illustrate this. 2 to the 5 we know is the number 32. Writing it in log form, we can say log to the base 2 of 32 is the number 5. Two specific index or exponential results you're familiar with. A to the power 0 is 1. If we write that in log form, the equivalent statement is log to the base a of 1 is 0. And a to the power of 1 is a. An equivalent logarithmic statement would be log to the base a of a equals 1. Now those two results are true for all positive values of that base number. Let's try some more numerical examples. Log to the base 5 of 25 equals 2. And how do we know that? Well, an equivalent statement in index form is that. Log to the base 10 of 10,000. Remember, the log gives the power that the base must be raised to give this number. That is 4. An index statement would be that. Log to the base 2 of 0.25 would be minus 2. That's the one that might catch you out slightly, so let's rewrite it in power or index form. 2 to the power of minus 2 is 1 over 2 squared, which is a quarter or 0.25. So the log of a decimal here has led to a negative. put another one over here. Log to the base x of 81 would equal 2. How would I solve that? Well, if I wrote that in a slightly different way, that's saying x squared is 81. So therefore x is 9. So that's using the definition. Let's just try a calculation one. Suppose I was asked to evaluate log to the base 10 of the number 20. Now that's not going to give me a nice easy number, because 10 raised to an integer power doesn't give me 20. So let's resort to a calculator. Just using an online calculator here. Log to the base 10 of 20 to 7 decimal places is 1.30103. Okay. Moving on to log properties. Well, the log properties are very much related to the index properties that you may well have met. There's not time, and the intention was not to go through the proof of those here, so I will simply state them and then do a few examples of using them. So I'll state the properties first and then illustrate them and how they're used with some examples. So the first log property, and it's a generalized base I'm using, it's true for any base. The log of xy is equal to the log of x plus the log of y. And this is sometimes called the multiplication law. We have the log of a fraction is equal to log of the numerator minus the log of the denominator, the division law. And then the log of something written in index form is the same as power lots of the log of the base. And this one leads to a particular result, that the log of 1 over, if we rewrite that as x to the minus 1, then the minus 1 becomes a multiplier, and so the log to the base a of 1 over x equals minus log to the base a of x. Those are the laws that we can use to simplify certain things. So let's have a look at some examples. Suppose a question says simplify the following. Log to the base 3 of 6 plus log to the base 3 of 7. Using the first multiplication rule, right to left, is the same as log to the base 3 of 42. And you could evaluate that on the calculator if you wished. Log to the base 2 of 15, take away log to the base 2 of 3, is log to the base 2 of 15 divided by 3, or in other words, log to the base 2 of 5. Log to the base 10 of 3 minus 4 log to the base 10 of 1/2. First of all, using this power rule, I get log to the base 10 of 3 equals log to the base 10 of 1/2 to the power 4, which is log to the base 10 of 3 minus log to the base 10 of 1/16, which is log to the base 10 of 3 minus log to the base 10 of 16 to the power of minus 1, which is log to the base 10 of 3 plus log to the base 10 of 16. And then using the multiplication rule, that's log to the base 10 of 3 times 16, which is 48. log to the base 2 of 40, take away log to the base 2 of 5 is log to the base 2 of 40 over 5, which is log to the base 2 of 8, which I could stop there, but if I realise that 8 is 2 cubed, then that's 3 log to the base 2 of 2, and log to the base 2 of 2 is the number 1, so my final answer simplifies down to 3. Solving equations of the form a to the x equals b. Well, let's take 3 to the x equals 20 for an example. Now these are invariably calculator exercises, but let's see how we proceed. We simply take the log of each side. Early scientific calculators only had base 10, so that would be the obvious base to use. When you see log, the accepted base there is 10. So if I take log of each side, and then use one of my rules to simplify that, I get this statement. If I then divide both sides by log 3, I get that x is log 20 over log 3, and that becomes 2.73. Now simple equations are very much like that to solve. Let's go for something a little harder. 2 to the power 2x add 3 equals 3 to the power of 3x add 2. Now again, if I take the log of each side, I get this. The power then becomes a multiplier because of that log property, so I get 2x plus 3 log of 2 equals 3x plus 2 lots of the log of 3. If I expand this out now what I want to do is I want to collect the expressions, the terms involving x together, and the terms that don't involve x on the other side of the equation. So I'm going to subtract 2x log 2 from each side. I'm now going to subtract that from each side, so I get 3 log of 2 minus 2 log of 3 equals 3x log 3 minus 2x log 2. I am going to simplify that just to illustrate some of the other properties. It is just a job for your calculator, so you could process that, but I'm just going to go a little bit further with that just to show these other rules. 3 log 2 is the same as the log of 2 cubed, so that's the log of 8. 2 lots of the log of 3 is the same as the log of 3 squared, so that's subtract log 9. The right hand side I'm going to factorise into x 3 log 3 take away 2 log 2. Left hand side, difference between two logs is the same as the log of a fraction. The right hand side I'm going to simplify as I did with this row moving to that row. That's the same as the log of 3 cubed, which is log 27, minus the log of 2 squared, which is 4. Log of 8/9 equals x multiplied by the log of 27 divided by 4, for the same reason that this became this. Now I could have bypassed those 3 steps. I would certainly need to factorise this to get to this expression, but from here I could simply divide that by that. Here I'm going to divide this log by this log. Really depends how fancy you want to be and how many marks it might be worth in a particular question, or whether you're just displaying your algebraic skill. So if I do this, I get minus 0.0617. 2 to the 2x, take away 6 lots of 2 to the x, add 5 equals 0. Now suppose I have to use logs to solve this. first thing I would do is write them all with same base and same power. So 2 to the 2x I know is the same as 2 to the x squared minus 6 lots of 2 to the x add 5 equals 0. I know this is the case because one number raised to a second power is the same as that number raised to the product. If I now let t equal 2 to the x, just so that we can see that this is a quadratic equation, you don't need to do that substitution, it's just so that you can identify it's actually a quadratic. So this would factorise into t minus 1, t minus 5 equals 0. So that means that t equals 1 or t equals 5. Go back to what I was calling them, then that's 2 to the x equals 1 or 2 to the x equals 5. This is very much like one of those simpler problems a few moments ago. If I take logs of each side, log of 2 to the x equals log of 1. Log of 1 is the number 0. So x log 2 equals 0 means that x has to be 0 is one solution, which you could probably have told by looking at that. The other one is that log 2 to the x equals log 5. X log 2 is log 5, so x is log 5 divided by log 2, which is the number 2.32 to 3 significant figures. That leads us on to the next mini topic, and that's the change of base. The change of base property is so that you can calculate a logarithm if the base is an unfamiliar base. As I've already mentioned, back in the days when calculators only had base 10, if it was something that required a calculator, you really had to change it to base 10 in order to use your calculator. Now that's not an issue. A lot of scientific calculators have the facility to change the base, but let's state the rule anyway. Log to the base a of x is the same as log to the base b of x over log to the base b of a. So as you can see, we've changed the base from base a to base b, and to do that it's log to the base b of the previous argument, the previous number, divided by log to the base b of the previous base. That's the rule, and we've got a special case, the special case that leads to another result. Let's say log to the base a of b is log to the base b of b over log to the base b of a. Log to the base b of b is the number 1. So what does that lead to? That leads to the result that the log to the base a of b is 1 over, or as the reciprocal of log to the base b of a. So let's just do a simple one. Log to the base 8 of 11 is log to the base 10 of 11 over log to the base 10 of 8, which on a calculator, we work those two things out, we get 1.153. If you don't like that way of thinking about it, go back to the very simple and initial definition of logarithms. This log to the base 8 of 11 is x. The other way of writing that using index notation is 8 to the x equals 11. We've seen this sort of problem before. Take logs of each side. Log of 8 to the x equals log of 11. X log 8 equals log 11. X equals log 11 over log 8. And that's where we came in with that property. So you don't have to necessarily in these sort of questions do that. You could write it as an index statement or an exponential statement and solve it that way. Let's look at a slightly more algebraic question. Suppose we have log base 5 of x plus 6 log to the base x of 5 equals 5. Now we've got different bases, and the way you generally solve a logarithm equation is to get the same base. So using that reciprocal arrangement, we get that's the same as 6 over log to the base 5 of x. If I now do that substitution, let y equal log to the base 5 of x, I will get y plus 6 over y equals 5, or in other words, y squared plus 6 equals 5y. Y squared take away 5y plus 6 equals 0 by rearranging it to get it into the standard quadratic way of dealing with things, which is y minus 3, y minus 2 equals 0, which leads to y being 2 or y being 3. If I now put back in what I'd substituted, log to the base 5 of x equals 2, or log to the base 5 of x equals 3. If I write that in exponential form, that's 5 to the power of 2 equals x, or 5 to the power of 3 equals x, which clearly means in this case x equals 25, or x equals 125. A common logarithm that you will meet if you take this topic beyond its definition is the natural log, which on a calculator is the ln, and that's the log with base e. If you want to do any research, that's Euler's number, and it's something in the region of 2.71828. The natural log, it's the natural log with a gradient equal to the reciprocal of the x-coordinate, if you like. If we think about it in exponential form, then the inverse function of ln of x, natural log of x, is what's referred to as the exponential function e to the x, and that's the function whose gradient is equal to its y-coordinate. I don't want to take that any further at the minute. I'll just leave that there, just to let you know that there is another particular logarithmic function that comes up a lot in the context of calculus. And just to finish off then, practical uses. Well, I didn't mention it initially. Logarithms are used in things like the decibel scale. Also, the chemists amongst you will know that the pH scale, to do with acidity of aqueous solutions, that's a logarithmic scale. Suppose we have two variables x and y, and you suspect that they are related by some non-linear relationship, a being some constant, x being some power that you're not actually sure what that is. Now what we could do, you've made your observations, you've collected some results of x and y, whatever they might be. If we took the log of each side of this expression, log of y equals log of a x to the n, using the properties we've talked about, that simplifies thus. This second expression, the n becomes a multiplier, so I get log to the base y equals, well, let me write it with this one first, n log x plus log a. If I now compare that with y equals mx add c, then clearly if I plot log y against log x, I'm going to get a straight line where the intercept is log a and the gradient is the power of the relationship at the initial outset. So that's one practical use if you suspect that they are related some way thus. A variant on that is if the relationship is something like y equals cd to the x, where x is the power rather than the base number, again c and d being constants. So if I take log to the base 10 or any base of the left and the right, same properties would lead to this being this, and again equating it with y equals mx plus c. This time a graph of log y against x only would give me some sort of straight line. Doesn't have to be positive gradient either, I'm just generalizing. This point here would be log c, and the gradient would equal log d. Once you've got these two values from the graph, it's then a very simple job to actually evaluate the numbers that would take you back to the original relationship. That's been a very whirlwind tour through logarithms. Leave any comments that you want that might clarify something. Please make them positive comments. Subscribe, come back regularly. If there's anything else you want, put that in the comments as well. I hope that was a useful little tour through logarithms. Thanks, bye.